Hey everybody, here we're doing our fourth recitation of the year, and today we're finally getting into some of the fun actual control stuff. I'm going to start making stuff work, especially with homework 2 just being released. So we're going to talk through LQR, which I know I've been saying this for every recitation, but this is like one of the biggest takeaways from this class, and it's pretty amazing the number of very difficult control problems that just LQR can solve. So it really is an amazing tool, and actually understanding it and how it works is really important. And then we'll go through change of basis coordinate stuff. How do I use LQR to control linear systems to different set points? How do I use linear control for nonlinear systems? How to linearize correctly? And then I'll be going through a Convex.jl tutorial, which is just the Julia package that we use to solve convex problems. And you'll be using this in homework 2 and the rest of the homeworks and hopefully in your projects and everything. All right, so let me just get cool. All right, so the first thing we're going to talk about is finite horizon LQR. And to do this, we have to talk about the number of x's and the number of u's, because you'll see different versions of this floating around. But just to be very definitive about what we're doing in this class, what we're always talking about is this discrete time system that looks like this. And so what this means is that if I have a trajectory of, I'm going to draw it out in a very Markovian way. So for those of you that have seen stuff like this, it should be familiar. So imagine I have a trajectory, an n step. You can think about it like this. I have n of these x's, and the way I actually get there is I have controls u. And so the way like these maps work is that, I use x to decide what my control input is, and then my control input combined with x gives me my new x2. So you don't have to really get hung up on this, but it's enough to know that we had this like causal dependency here where information from x is going to tell us what we do for u, and then these two together will combine to create x2. So if you've ever done like a Markov decision process class, you'll see tons of these plots. This one is super simple. It's just showing us that we have a control and a state, and they both provide information to get us to our next state. And the main thing that we should know is that when we talk about the number of x's and the number of u's, let me make this a little bigger. Xn minus 1, u n minus 1. So if I'm dealing with an n-step trajectory, really what I have is I have n x's and I have n minus 1 u's. And so this is something that you'll see people do a little differently. When we are talking about the sort of control problems that we care a lot about in this class, we are always dealing with this. There's one exception in which we'll do this in a few weeks, but we'll make it very clear why there's an exception and what this actually means. But for LQR, what we're getting to right now, what we got to focus on is that we have this relationship between x and u, and they come together to form the next x as far as the flow of information. So if I need to represent an n-step trajectory, I need n x's, I need n minus 1 u's. And with that, this is the real takeaway. So with that, we can now get started on, and I'm gonna give you all the different names of this. So here is finite horizon LQR. Now, LQR is a linear quadratic regulator. You will also see this as time varying LQR, discrete horizon LQR. People will call this many different things, but you just have to recognize the cost function and know how to solve it. So let's form the optimization problem. So if you remember, if I'm solving over an n-step trajectory, I have x1 to n, put a little lower. And then because it's an n step, I have n minus 1 controls. So 1. And now let's talk about what our cost function is. So let's do a sum equals 1 to n minus 1. And here I'll have xi transpose q. And I guess I'll be as general as possible. So these can be different cost functions, but they rarely are. But I'll just leave it like this because this is what we normally see. So this cost right here, this is what the sum is, and then plus, and I'll add a 1/2. Generally, it's nice adding 1/2. The reason why is that when we go and take gradients of this, we don't have twos floating around. So if you remember when we did our stuff with the quadratic form, if I have like x transpose q, x plus q, and I put a 1/2 here, I take the gradient of this, I get just qx plus q. So, this 1/2 falls out when we take the derivative. In the same way that we had like 1/2 x squared, we would just get x. So it's very common to put a 1/2 in front of these cost functions. And the last part of our cost is xn transpose qn x. So what do these actually mean? First, let me write down the constraints, and then we'll look back at the cost function and give it the names. So now the constraints that we say, subject to, or such that, there's some debate over like which one it is. I don't think it really matters. X0 equals, and this is just initial. So we're saying that, all right, I'm given some initial condition of how I want to start this simulation where I currently am, and I want to solve for a nice trajectory that gets me somewhere else. In this case, going to get me to the origin. And then our dynamics constraints are x k plus 1 equals a xk plus b uk. And then I'll just do, for k equals 1, 2, and minus 1. All right, so this problem, while it may look simple, it's super important to understand like what all these pieces do. So the first thing we're looking at here, this is what's called our stage cost. And this is terminal cost. And then we have our initial condition constraint saying start where we're supposed to start. And then we have our discrete time dynamics. So how does the system move over time? So at a very high level, what we're looking at here is that I want to solve for a controller. I'm given some system, you give me the dynamics of some system, and then we give ourselves this cost function. And what I'm trying to use convex optimization or just generally numerical optimization. I want to formulate my control problem as an optimization problem. And that's, as the theme of the whole class is that I always want to take my control problems and do some concrete numerical optimization to give me what my control input should be. And so a really nice way of doing this is I just take the dynamics, I take my cost, and I just put it into an optimizer, and I say, give me the solution to this. And as you can see, this is a convex quadratic cost. Let me make a for LQR, not in general, but for LQR, I need Q to be symmetric, positive, definite. Or it can be semi-definite. Let me draw my inequality better. So positive, semi-definite, positive, definite. So if let's just assume you should always use this for your control problems. There's no scenario in which this should be semi-definite because it means there's certain control you can do that don't show up in the cost function whatsoever. So if you remember what it means to be positive semi-definite is this means that I have some eigenvalues that are all positive, but some that are 0. And what that means is that if I have a 0 eigenvalue, the eigenvector associated with that eigenvalue results in 0. So if you imagine if R had a 0 eigenvalue and U was that eigenvalue, this term would be 0. So I could have like control in a certain direction that didn't incur any cost. So there's going to be a quiz question on this, should be relatively straightforward. The idea is that any sensible controller is going to have stuff here because I don't want any control U that doesn't cost anything. I don't want any free controls. They should all be penalized somewhat. And then this, we can do whatever we want to. Say we want to penalize some states, but not penalize others. That's totally fine because we're not directly controlling the X's. We are directly controlling the U's. All this to say, this is the condition that we want when we form our LQR cost function. So now with this problem right here, this is a nice convex optimization problem, and it's the absolute easiest type. So in the world of convex optimization, there's unconstrained quadratic problems, very easy to solve. Then there's equality constrained quadratic problems, also very easy to solve. So this is equality constrained QP. And we can solve this with the linear system in closed form. So for the expense of one linear system solve, I can solve this to closed form, which is amazing because this means, again, in the world of convex optimization, this is the best thing we can do. So now with that, we can move on to, now that we have an understanding of finite horizon LQR, time varying LQR, let me make one note right here. And this is, I'll use a different color for this. So time varying LQR, I'll put in green. What time varying means, so first off, if it's varying over time, that means we're talking about discrete trajectories. But most importantly, it means that these A's and B's are going to change over time. And again, this is still an easy problem to solve. It's still a nice, equality constrained convex program. But this is saying that we have a different A and B for each time step. So if you imagine, earlier in the class, we had a quiz where we gave you A's and B's that were time varying, and I asked you, is the resulting ODE still linear? And the answer is yes, right? We're allowed to do this. We can make our system more expressive by giving it time varying terms. And the way we've written down this problem, without any loss of generality, we can say that A and B can change over time. Now, sometimes this will be the case, sometimes it won't, but either way, it's the same algorithm. And now let's talk about infinite horizon LQR. And this one takes, I think, a little bit of a second to fully understand what we're actually doing here. But imagine that if I took the finite horizon LQR policy and say I want to solve for a trajectory of 10 time steps or 20 time steps or 100 time steps or a million time steps, I can make this thing up to infinity. So I want to, now this problem I'm writing is weird because it's not, you'll see in a second, it's, u to infinity minus 1 doesn't really mean anything. And then our cost is just xi transpose. Let's just say infinity for both. I will do the infinity minus 1. And then we have our same. So here's our infinite horizon LQR problem. And what I'm saying is that I want to optimize this trajectory from now until the end of time, which is weird. We can't solve this numerically anymore because we no longer have a discrete or a finite length trajectory. We're talking about an infinite trajectory. But it turns out we can still solve this problem. We just can't solve it with traditional convex optimization. So this is the infinite horizon LQR problem, and this is where I'm dealing with trajectories that go on forever. Now, when would you use one versus the other? So imagine if I had a plan where I wanted to drive some system over the next 10 seconds. I wanted to drive this system to some equilibrium point. I would use finite horizon LQR because I'm worried about a specific finite horizon. But say I have an infinite horizon problem, and where these show up is if I have, a regulator that's doing something. So I have a cruise control in my car. I'm not going to tell the car how long I want to have cruise control on for. I just want to press a button and say control to 65 miles an hour, and it'll just control like that forever. So for systems where you need this controller to basically run forever, which a lot of controllers in our real lives actually do, whether it's a building HVAC control, cruise control, the thermostat in your house, a lot of these controllers do run forever. So having a cost function that reasons about forever is actually pretty useful, and it gets us pretty far. And those are the two, I guess, the first two types of LQR that we're looking at. And so I'll just make some quick notes here. Then Zach went over all this in class. So infinite horizon, LQR can be solved with Riccati. This is what Zach went over in class. We do the Riccati recursion, and we get a feedback policy that is optimal everywhere. Finite horizon, LQR. Ooh. So infinite horizon LQR, we have to solve this with Riccati. Finite horizon LQR, we can solve it with Riccati, or we can also solve it with convex optimization. So we have two options. And there's a little bit of a difference in the way that we represent the solution to these. So normally we're used to seeing, when I write down a problem, I'm just getting a solution that just tells me what is X and what is U. And when we use the Riccati recursion, we get something a little bit different. We get a feedback policy. So when we solve for Riccati, what we get is we get ui equals negative ki x for finite horizon OQR. Then we get ui equals. So the difference here is that in the case of finite horizon LQR, I have a different gain k for every time step of my trajectory. And for infinite horizon LQR, I have the same, just one static k. I use that forever. So you imagine how appealing this is as a solution method for a control problem. If I was building a cruise control, I could just, get a linear model of my system, say I want to optimize this thing forever. I get just one matrix K, and then I load this like just a 2D matrix onto my robot itself and tell it to run. This is like about as simple as it gets. And you would be amazed at the number of problems that are really complicated, high dimensional, all sorts of crazy stuff, and we can just solve trivially with infinite horizon LQR. Or if we're talking about, a specific time trajectory we're looking at, finite horizon LQR. And if you've taken a classical control class where you did a bunch of, frequency domain stuff like root, locus, and Bodhi, you know how tricky it is to not only get a system to be stable, but also to solve a system that has multiple degrees of freedom. And this just does it. It will always give you a stable controller if one exists. It is always optimal to the cost function that we wrote down. And it's, again, just amazing the number of things this can solve. So this is why we keep talking about it, because you'll get so much mileage out of this. Now, when we talked about the way we can solve finite horizon LQR, I said I can solve it as a QP, or I can solve it with Riccati. And let's talk about what those look like and why we do one versus the other. So time variant LQR, one is I can solve a QP. So I can say U equals argmin So at every time step, I can form and solve this QP. That is my first option. My second option is I use my feedback policy that I solve for with finite horizon LQR. So let's think about why we would maybe want to use one versus the other and potentially maybe never use one of them. So if I think about my state space, this is, x1, x2. Here's the origin. So, so say I start with some x naught over here. So if you imagine if I have an x naught right here and I use option 1 for solving for my policy, if I minimize this convex program and I get my first u and I execute that u on the robot, maybe it moves here to this new spot of x1. but my model is a little inaccurate, my actuator is a little inaccurate, there's maybe some noise in the system, some unmodeled disturbances. There's a million reasons why the control that you execute won't move the robot or move our system to the exact state that you thought it was going to. In fact, you will never find a robot that does do this perfectly. So it'll move a little bit off where it was supposed to. And what happens there is that now that I have moved off the course of my trajectory, I can't use U2 because I'm now at a different point than the convex program thinks that I was. So when I solved this problem right here, and I solved over a discrete time trajectory, I assume that, my dynamics are going to move as my linear model says they're going to move. And when I go and practice and it turns out that there's a little bit of error after the first step, I can keep running this thing open loop, as you call it. I can just keep feeding it new controls and have it run. But the problem is I'm not taking into this state error that I'm getting every time. And so we'll end up doing weird stuff. And alternatively, what we want is we want a controller that takes us to the solution. And that may be a little different than the thing that our finite horizon solver told us to do. So the beauty in this is that with a feedback policy, I don't have to resolve anything. It is not a function of the state itself, how I figured out K. I'm thinking about a trajectory of a certain size. I solve for those Ks, and now I have a feedback policy that is totally fine with any sort of noise, uncertainty, anything. It'll just take that and just give me the resulting feedback term. Or in this case, I have to resolve this problem every single time. I'll add a note. This is solve a QP. And this is just matrix multiplication. So from here, we talk about how, we solve this problem in two different ways. We can either solve it with convex optimization, or we have to solve a QP every time our state changes from what our planned out trajectory was going to be. Or I can just use Riccati. I can get a feedback policy, and this will just work no matter how much, well, it won't work for any amount of model uncertainty, but it will work no matter where we are in the state space. And that's super important, that this is option 2 is going to be globally. And this is something that we'll explore a little bit in Homer 2, but this is super awesome. As far as controllers go, we have a linear system, and I'm saying no matter where you start on the state space, when I did Riccati, nowhere in there did I take any sort of information about what my current state value was. I just said, here is my cost, here are my dynamics matrices. We do a recursion, I get a feedback policy K for every time step, and it does not matter where I start in the state space. This is always going to be the globally optimal answer. And this thing right here, this is specific to just the initial condition I gave it. So this is a pigeonholed a little bit where this solution is only useful if my initial condition is where the robot is. This is useful no matter where I am in the state space. And that's why this is like so powerful. So now the next thing we're going to talk about is using LQR to drive us to goals. So in everything we've written so far, our cost function has been, minimize this thing with respect to the quadratic cost that just puts a penalty on everything. So it's going to drive the system to x0, u0. That's really where it wants to be. It wants to be at a point where nothing's happening. And that is not always possible. So let's talk about when we want to change these coordinates, if you will, to drive it to a separate goal. So if I have a cruise control on my car, I want to set at 65 or set at 75, set at 50. I can set a desired speed. So again, if we have xk plus 1 equals a, xk plus b, uk. So now let's assume I have some set goal control I want to move to. So I want to drive my system to be x goal, u goal. And what does this mean? This means that I want x goal equals a So what does this mean right here? This means that This means this. This means I want to drive it to some goal where the system is at an equilibrium. So when I do my normal, give it xk, uk, get xk plus 1, I want to give it my goal state, give it my goal control, and have that keep me at the goal. So this means that I have some x goal I want to drive the system to, and there's an x goal and a u goal that's going to keep me at this goal. So now I'll define some new coordinates. I'll just say two things in terms of tildes. And again, I'm not solving for anything. I just made these up and I'm just saying, here's are some tildes. Here's what they mean. U tilde equals U minus UG. So now let's work out what are the dynamics of our new system as represented in this tilde form. So we do X tilde K plus 1. This is XK plus 1 minus X goal, right? This is me just taking this definition and then applying it to a time step of K plus 1. And then now let's do a little, so I'll do blue for this, red for this, and then blue for this, red for this, just to see where these things come from. So now I'm just going to substitute in what I have up here, which is AXK plus BUK. And then if I look at what my X goal was, this would be minus. My X goal is going to be I'll just use XG for goal. Save us the pain. So we're all in agreement thus far. I said that, here's our normal dynamics function. I want to drive to some goal where the state does not change. It stays at the goal once I get there. I define what these tildes are. These are just new tilde coordinates. And then I just said, okay, let's take, the definition of our tilde at xk plus 1. Let's substitute in our dynamics for here, and then substitute in our goal for here. Once we get that, we can just do um, and we recognize this is, again, x tilde, and this is u tilde. So I'm back to my favorite form. So now in terms of these tildes, I get the exact same thing as before. So now I can just do, k equals, infinite, or just any form of LQR that takes our A, B, QR, QN. And this feedback policy now applies to any goal I have. So all I did right there is I showed that if I want to talk about driving the system to a specific goal, I just went and I substituted everything in. So I have like these tildes. I go and I sub those in. And what I get is I get a linear system that looks the exact same as before, but opposed to being x's and u's, and I'll have x tildes and u tildes. So what does that mean? That means that my control policy is going to be u tilde equals negative k x tilde. And now let's look at what this actually means. So u tilde, if you remember, this is u minus u goal, negative k, x tilde, this is x minus x goal. So our actual policy is u equals u goal minus k and this is how we use any goal or X goal. So I find the spot in the state space I want to go. I figure out what control I need to keep myself there. I have an X goal and a U goal. And then I go ahead and I just throw this feedback policy in there. And again, as you saw, when I solved for what this feedback policy was, I didn't need to know anything about what my goal was. Nothing, none of the inputs here have goal. So let me put. So I did not give my LQR solver, whether it's a Riccati solver or whatever, I did not give any information about what my goal is. I just have this K. And so what this means is that I can change this set point however I want to. So if I'm in cruise control, I can add miles per hour on my speed. And I can say control to 70 or 75 or 65. And I don't have to resolve for this K. And again, this is pretty amazing because what I showed before is that not only is this thing optimal anywhere in the state space, so no matter where I start, I can optimally drive me down to the origin. But I now said that not only can I drive myself to the origin, I can drive myself to anything that's actually feasible. And this is pretty amazing. With one call to LQR, I have a globally optimal policy that can start anywhere and can finish anywhere. And that is why it's so amazing and so versatile. And let's see, what should I go over next? So I think next it would be nice to go through, I guess, how this works for nonlinear systems. So first I'm going to go over some delta stuff. So if I do the exact same derivation I just did, but opposed to using tildes, I use deltas. I'll show this I'm going to run through this because this is exactly what we just did, but xk plus 1 equals a, xk plus b uk. And if I say I have some goal, my classic goal thing, plus b u goal, and I have some new coordinates that I say x goal which is so I did the exact same thing before, but now I just use delta as opposed to tildes. So I just used a different change of basis. And I got this right here. And this is important because what I'm about to do is a nonlinear system where how we linearize and the deltas we take actually make a pretty big difference over what the controller looks like. And this is going to bring us to LQR for nonlinear. So let's go over our general nonlinear system is xk plus 1, f xk uk. This is our just a general nonlinear system. And now let's linearize about something. So say I have some equilibrium point I want to drive this nonlinear system to. And at first, we'll just talk about as like a static point, like a general individual x bar, u bar I'm looking to. So I have some x bar, u bar. And you'll see Zach use bar when he means linearize about. When Zach says let's linearize about it and use a linear controller, what I'm about to go through is what he means when he says that. So let's just assume this is an equilibrium. What that means is that it doesn't change once I'm there. So once I reach x and u, it's going to stay at x and u, and I should be happy forever. So now if I take my dynamics function and I linearize it the way that I would linearize anything, which again, I remind you is if I started with this right here, this is my original function, and now I want to linearize this thing. I want to do xk plus 1 is approximately equal to, okay, linearize about these values. Now I take some derivatives. df dx at x bar u bar x bar u bar.
These values that we will these points that we will linearize about are the goal points.
Yeah. So they can be goal points. They don't have to be though. They can be anything, and you'll see that we'll use them all over the place. But in this example, just to start, let's assume this is an equilibrium. So x bar u bar, when put into our dynamics function, keeps us at x bar. So for now, we can think about it just as if it was a goal.
Okay.
Sound good?
Yep.
Okay. So here's our uh so here's our first order linear model. And now let's do another game where I am going to think up of a new set of coordinates. So now let's say that x is x bar plus delta x. Now again, whenever you see me write down one of these like new definitions of coordinates, I'm not deriving this from anything. I'm just saying this. I'm just saying, okay, introducing some deltas. What do the deltas mean? It's just the difference between our actual state and this x bar. So these are not derived from anything. I'm just woke up one morning and just decided that this was true. So I'm creating a new variable, delta x and delta u, and I'm just saying, here's what they mean. And now let's go through and let's substitute in these new coordinates into our first order Taylor series and see what this gets us. So x k plus 1 is about equal to x bar u bar, and then plus, and just to make the notation easier, this is a, this is b. So I'm going to use a and b now when I'm talking about these things. A x bar plus b x bar. Now, if I substitute in my own stuff, what I see is I get, so I just replace everything with the deltas. And now something cool is happening. So I see that this x bar, this shows up on both sides. And if I assume that this was an equilibrium point, so if this is true, then I can just remove both sides of this equation. Now, this isn't always true, but for most cases, and what you'll do in homework 2, you're going to have an equilibrium point, x bar, u bar, that you want to drive it to. And so these can just get canceled. And now I'm left with the system in our absolute favorite form. So once again, now that I have the system, and before what I did is I showed you that this thing can be in terms of tildes. So in this case, I showed that, when I was driving my linear system to a goal state, that I could just, introduce some new variables, tildes, work everything out. And turns out when I solve LQR, it doesn't matter what basis this is in. And I guess basis is maybe not the most, I guess like the clearest way to say this, but I have an LQR controller that I solve for that's just a function of A, B, and my cost, but nowhere in there does it have to know where I linearized about, where I am, all this stuff. I don't need to know any of that. So what this means is that I have a system in my familiar form. Doesn't matter there's deltas. All it means is that I can just use LQR again. And this gives me the following policy. Delta U equals negative K delta X. And I go and I substitute in our stuff. And what we see is that um, what we see is that when I substitute in these deltas, there it is, I get U minus U bar equals negative k x minus x bar. So what is my resulting policy? U equals u bar minus k x x bar. And this is really important. You will see this all over. People will forget to do this, or they'll forget to do this, and their controller just won't work at all. So it's okay that I can do LQR and, in the deltas or whatever, but then my actual policy is going to be in the deltas because this LQR function right here is just assuming A, B, and the cost information, and it will specify a feedback policy in this form where these variables are whatever variables we use to get this linear system. And so then from here, you just add in your definitions of what the deltas actually mean. And now we recover our feedback policy in terms of U, which is our actual control, not our delta or anything. And the reason this is so important and why, I guess the caveat for nonlinear systems is that if I think about a big state space, makes it a little better. If I think about a big state space, say this is x1, x2, our LQR controller is globally optimal. For a linear system, it does not matter where I start, LQR is optimal everywhere. Now, if instead if I linearize my system and I'm using LQR for a nonlinear system, LQR is really only optimal where that model is true. So a very small very small region of the state space. So really what I get just around where I linearized, I get LQR for nonlinear system is kind of. So in the terms of normal LQR for a linear system and a full state space, LQR is globally optimal. If there is a stable controller I can get, it is a stable controller. This has everything I'd want out of a controller for linear systems, globally optimal, always stable. For nonlinear systems, we're really only optimal exactly here. And this is because our linearized version of the model is only accurate right here. And the further we get from it, the less accurate that linearization is, the less accurate that first order Taylor series is. And then it will reach a point where not only does LQR no longer optimal, but it's no longer stable at all. And this is super critical. So we'll do this in the homework where we show that, LQR for a linear system works everywhere. I can start anywhere. I can drive to anywhere. It all just works. And then for nonlinear systems, if I want to linearize the nonlinear system and use an LQR controller on the nonlinear version, it really is only optimal at exactly that point. And this is fine in most cases because our controller, we want to drive it to that point and stay there. So if it's suboptimal in the region around it, that's okay as long as it's stable and can recover. But there's certainly times where you can go too far away and then the controller is no longer stable. And you'll do this in the homework. In the homework, we'll do a cart pull example and we're going to linearize about the pole when it's up at the top. So if you imagine the linear model is pretty good once it's up here, and it gives it this amazing ability to correct relatively large errors. You start it here, bring us right back. Start here, bring us right back. But then I reach a part of the state space where if I start here, the model is not good enough, and my controller is so inaccurate that it actually drives me away, and the system ends up doing bad things and blowing up. And this is one of the big takeaways from the class. LQR for a linear system, the best thing ever, optimal everywhere, can drive to anywhere. LQR for a nonlinear system, it can be amazing, but it really is only accurate in the region in which we linearize the system about. And it's not quite optimal, which is fine for our cases because it normally works just fine. But it is important to know that LQR for nonlinear systems is very much a hack, but it's a hack that works extremely well and again can solve just amazingly difficult problems with other techniques. So I'm now going to transition to going over some Convex.jl stuff. This is the Julia package that you'll be using for homework 2. Zach will be using a little bit in class, and we'll be using it for the rest of the class and the rest of the homeworks. So I'm going to stop this share. Any questions while I transition? Cool. So now we'll just run through this. And all this code, I'll put it up on the website so you can see it. So the idea with Convex.jl, this is like, I know I keep hyping up LQR, keep hyping all these things up. Convex optimization is awesome. It is in the world of optimization, there's convex and non-convex, and you can really interpret that as things we can solve and things we can't guarantee anything about. So doing things that are convex is very nice. And the software around convex optimization has gotten so good in the last 10 years, even the last five. Um, and we can basically form whatever problem we want to, and then just hand it off at a very high level to something else to actually go down and build it and solve it. And so what you have is you have these problem parsers or problem parsers and canonicalizers. What this means is that, a specific solver may want to see a problem in a very specific form. So the matrices must look like this, the inequalities must look like this. But often that's not kind of how we think or how we think about control problems or just general convex modeling. So what there are is there's a bunch of these awesome tools that let you just write down normal optimization problems with math, and then behind the scenes, it'll convert that into a standard form and use a solver to do it. And it dramatically lowers the barrier to using these solvers, and it's pretty amazing. So Convex.jl, this is the Julia tool. They're pretty much all done by Stephen Boyd's group at Stanford. He's the guy who wrote the book and everything. And today we're using a solver called ECOS, which is a primal dual interior point solver for conic problems. We don't have to know what that is yet. But basically, it doesn't matter what language you're in, these things exist. So for Python, CVX is the most popular. This is actually the most popular of all of them. This one's is the most actively maintained. It's probably the most performant. CVX opt is a much older version. CVX is probably what you want to use. For MATLAB, you can use CVX. This is the original. So all the older Boyd classes until like 3 or 4 years ago all used CVX. So again, if you're in MATLAB, CVX is awesome. YALMIP works just fine, but is a little less popular. R, we have CVX-R. All these things are, you can use whatever you want to for your project. But for this class, since we're doing things in Julia, it's convex.jl we use here. Here's the repo. Here are the docs if you want to read through them. It just is a tool for formulating and solving these problems, and it interfaces with all these solvers. So what's nice is that because people like using these problem parsers, when I write a solver, I will write an interface to this parser, and I will say, hey, I want people to use my solver, so I will make it play nice with your problem parser so people can actually use it. So here's just a bunch of solvers that maybe you recognize some. Some of them are commercial, some of them are open source, and they all interface with these tools. So here's a very simple example. If I want to minimize this least squares problem, so, AB, the way I create a variable in convex.jl is with this cvx.variable. And again, I imported convex as cvx, which you don't have to do, but I like doing. So this is how I create a variable that says I want to solve for a length 5 vector. I want to minimize sum squares. So again, sum squares, this is the same as norm squared or dot of the vector times itself. If I use either of these, it'll complain. It'll say, I don't know what to do with that. So you have to specify it in sum squares. Then I solve the problem. Silent solver false just means give me the input as you're solving it. And this is the output from ECOS, the solver itself. It's going through the iterations inside the solver until it reaches convergence criteria. The way to read these is it's very problem specific, but this is our primal cost, dual cost. These should be the same once we're optimal. So you notice how they start different numbers and towards convergence, they become the same number. Gap, this is the duality gap. So how well is complementarity satisfied? So it starts out not satisfied at all, and then by the end of it, it's very close to machine precision. Step is just saying like how large of a Newton step am I taking? You generally want this to be like nice and healthy. These numbers are totally fine. That's in a sense how to read at least the ECOS outputs. Here's another problem. Say I want to minimize the norm of x subject to a constraint. So now I'm constraining ax must be equal to b. So again, I create my variable using the same stuff. I minimize sum squares of x, and then I add a constraint with the following. So prob.constraint is going to hold all my constraints, and I can just use plus equals and add a new constraint, which is a very nice interface. So I want to add that ax must be equal to b, and I have to use two equal signs to show equality. And then do the same thing with my solver, solve it. Everything looks good. Now an equality constraint QP. So again, I can solve this very easily with the linear system, but then I have to do some indexing and build some stuff, but not a problem. But either way, I can just use this. So I can say x equals cvx variable. I'm solving for a length n vector. This is really important. Quad form is the Convex.jl way to do a quadratic cost. So again, if I wrote out the naive quadratic cost, it would give me an error, it would complain. But I use quad form to do this, and it just works. Minimize, add the constraint, good to go. So everything I've done so far has been like relatively close to standard forms, so it wouldn't have been that difficult to take that problem and put it in your own form. But here's an example where there is no standard form, and this would take some manipulation and slack variables and all this stuff to get us to solve and put it with a normal solver. But these things just do like behind the scenes. So say I want to minimize the L1 cost of this. So this is not a linear or quadratic cost. This cost is not in quadratic form right now. And then I have another constraint that says, okay, the norm of x must be less than 3. So this is all convex. This is still a convex optimization problem, but there is no standard form that this is close to right now. The only way to transform this into a standard form would be to add some slack variables and do some finessing and have some new variables and put it into a solver like this. But with convex.jl, it'll just do it for you. So I solve for this vector of length 5. I want to minimize the L1 norm. Here's how I do L1 norm. And then the constraint is that this L2 norm of x must be less than 3. Again, this just works. And you see like how fast this is happening. Like for all like sorts of homework, prototyping, everything, this is just the best tool ever. And everything we've done so far has been solving for individual vectors. So we haven't really strayed that far from normal optimization stuff that we've seen this far in the class. But now is where it gets like a little weird, and this is where it becomes super useful to us. So say I'm solving like, that LQR problem, but here I'm just doing a generic convex trajopt problem. So I have a bunch of weird, funky constraints, and I'm solving over opposed to just one vector. I'm now solving over this vector x for every time step 1 to n. And I'm also solving for u from every time step 1 to n minus 1. So now I'm not just solving for a vector. So if I had to solve this with the solver that I wrote, I'd have to take all the decision variables, stack them up into one vector, do a bunch of crazy indexing, make sure everything is where it's supposed to be. Or I can just do it like this, which is why this is just so amazing. And once you start working with this and kind of do it both ways, like try doing it yourself and then try letting convex.jl do the parsing, you will really start to appreciate this tool. So what I do is I'll create a linear system, make sure it's controllable, which is, Zach went over this in class yesterday. Um, I have 20 time steps. Here's my initial condition. Here's my goal condition. Have some terminal cost. And now I create my variables I want to optimize over. So normally we're always optimizing over just one single vector, but here I can just optimize over whatever I want to. So here I have just a nice big matrix that contains all my x's for each time step as each column, and then u's, where each column is a new u. And so this is just, xk is going to be xk, uk is going to be uk. So now I create my cost. So here's my LQR cost. Here's my stage cost. So I'll just do stage cost as I go through from 1 to n minus 1. And here I add this, and then the L1 norm of u, because as you can tell in my cost function, I had this really weird thing right here. And then my terminal cost. Where I use my QF. And I want to minimize this cost function, and now I have to add my constraints. And I have a bunch of constraints. I have my initial condition constraint. I have my dynamics constraint for each I n minus 1, goal constraint, norm of u less than 3, and then bound constraints on x. So everything I just wrote down is still convex, totally solvable, but it would be an absolute pain in the neck to put this into a standard form solver. So using one of these parsing tools is just, again, just magical. Like I can't express how amazing this is compared to doing it yourself. Initial condition, add our dynamics constraints, add our goal constraint, add our norm of the control less than 3. Then here we add our state constraints on the bounds. Let me go ahead and solve this problem. Again, solved in no time, solved in 2 milliseconds. And even this is so much slower than it'd be with a custom solver. But we're talking about convex optimization, which is so fast in general, that for prototyping, playing around, doing control stuff on homeworks, everything is just much simpler using one of these parsers. So I'll post this. This is pretty much, I mean, you can go through, read the docs if you want to. Everything that I did in this notebook is going to pretty much cover everything you would need to do in the homework or on a project or whatever. But by all means, feel free to read some other stuff. But my idea was to kind of give people this and have them with just this be able to complete the homework and everything. So that is, I think, it for today's recitation. Any general questions on LQR homework stuff? I know homework one was due last night. Seemed like it went pretty well for most people, but always open to feedback. And then after this, I'll start my office hours at 9, where I can just talk for an hour for whatever we need.